Hi, today we're doing half reactions. Now, disclaimer, if you are not a pro at finding oxidation states, go watch that video first and then come back here because you really need to know how to figure out oxidation states before you can be good at this. And I'm not trying to be mean, that's just the way that it is. I'm sorry. So here we go, half reactions. Sometimes the best way to figure out if something was oxidized or reduced is to write the half reaction. So we're definitely going to need it later when the stuff gets a little bit more complex. Now, this reaction I showed you in the last video, not a half reaction. This is a full reaction. A half reaction will just show you what happens to the chlorine or what happens to the hydrogen. And those two things, two halves make a whole, two half reactions for every reaction. Here's how it's done. The first thing we would do is determine the oxidation state of all of the atoms in the reaction. I'm going to give you the steps first and then examples. Then what we're going to do is we are going to look for changes. So somebody's oxidation state should be going up, and that's the guy who's losing electrons. Remember, if you kick negative people out of your life becomes more positive. So if you kick out electrons, your charge is going to go up. And then conversely, somebody's charge should go down. That is because they are gaining electrons and electrons are negative. So the charge goes down. So the guy whose losing electrons, you should remember, is being oxidized. The one who is gaining electrons is being reduced. Now, we're going to write that element on both sides of the arrow. We're going to put the charges with that. And then what we're going to do is balance with electrons. And this seems a little funny, but so far you have been balancing your reactions in terms of mass. So you need the same number of each atom on both sides. And this thing that's in my eye, driving me crazy. Now what you need to do is start balancing in terms of electrons. So what that means is that not only do you have the same number of atoms on both sides, but you have the same amount of charge on both sides. Now, what does this look like? Here we go. This is a single replacement reaction because we have chlorine coming in and stealing the hydrogen from bromine. So if we go through and we remember all of those rules from determining oxidation states, here we have chlorine all by itself. It's a diatomic element. That makes its overall charge 0. In this situation, hydrogen is going to be +1 and bromine would be -1. And then here, hydrogen's +1, chlorine is -1. And then bromine, again, diatomic element all by itself, overall charge is 0. Now, you should notice that hydrogen's charge stayed the same. Hydrogen didn't do much in this reaction. Then we have chlorine, whose charge goes from 0 to -1, and bromine that goes from -1 to 0. Circled here. So if we look at the chlorine, specifically, this is step 3. You would write it on both sides of the arrow with its charge. I'm not writing the 0 because I'm lazy, like a chemist. So there's an imaginary 0 up here. And then on this side, we have a -1. Now, I already know that I have 2 chlorines on each side here. It's balanced in terms of mass, but not in terms of charge, because it's 0 over here and it's -1 over here. And that's not cool. Then same thing is happening here. I take the bromine from the reactant side and really just give it its own reactant side here. I'm going to carry this 2 from the original equation because there's 2 bromines in this equation. It is a -1 overall. I'm sorry, my face is so itchy. Oh, allergy season. And then we have diatomic bromine over here with, again, an imaginary 0. Last step is to balance using electrons. So in my chlorine situation, over here I have -2 in total on my right side. I need to get -2 also on my left side. So what I would do is put 2 electrons over here. This means that chlorine 0 is going to add in electrons to become chlorine -1. I need 2 electrons, 1 for each chlorine. And then over here, it's the opposite. The bromine -1 had to give away 2 electrons in order to become bromine 0. Again, bromine had to give up electrons in order to become bromine 0. Okay, now we're going to do it. That's the 2 half reactions. That's it. So we're going to do it with this reaction here. Again, we have another single replacement reaction. We have, let's roll. I'm just going to skip to what's easiest first. So I'm going to slide the cursor all the way over. Hello. I don't even know. Here. I'm going to slide this all the way over to the copper. Because this is an element all by itself. Its charge is 0. I have copper. Oops. Too far. Not copper. I have silver over here, which is all by itself. So that would be, again, 0. Now, if I look at this, I'm just going to look at the nitrate in this case because I know that the nitrate's not changing anything because the nitrate's not breaking its bonds. It's nitrate on both sides. So that's how I know I can take the shortcut. If I were to uncrisscross this, remember there's an imaginary 1 right here. The nitrate's overall charge is -1. You can find that on table E in the New York State reference tables. And then after the nitrate, remember that's a polyatomic ion, there's an imaginary 1 down here. So silver is going to be, silver is going to be +1, and my nitrate is going to be -1. That's not for the nitrogen or the oxygen, that's for the nitrate. Maybe I'll write that. Now, I know that I can just look at the nitrate because the nitrate itself is not breaking or forming bonds. Silver, on the other hand, was bonded to nitrate, and now it's not bonded to anybody. So I know that its oxidation state is going to change. The N and the 3 O's don't break apart, so that's for the nitrate. Then we have the copper is 0. If I look at the copper now and uncrisscross it, this copper is +2, and this nitrate is still going to be -1 because there's an imaginary 1 right behind the copper. And I'm going to indicate again that that is for the nitrate. And then we have our silver is 0. So if I look at this, I could very easily identify that my silver is changing. Silver is going from, nope, I don't want to fill it. I want to outline it. Thank you. Silver is going from +1 to 0. And then the copper is going from 0. Let's try pink. 0 to +2. So I can tell here that we have an oxidation and a reduction. So what I'm going to do, I'm going to steal that, and I'm going to put it right here. So step 1 is find the oxidation states. 2, look for changes. 3 is write them with their charges. So if I were to do that, we could even do this. If you want to see the 0 up here, that's fine. So we have copper 0 changing into copper +2. And I also have silver +1 turning into silver. Ooh, what did I just do? Turning into silver 0. So, wrote my elements and I wrote their charges. Now I need to balance with electrons, and this is the hardest part. So if I'm looking at my coppers, I have copper 0 turning into copper +2. If I were to put +2, let's expand this and center it the best that we can. if I were to do this and I put my electrons on the product side, 2e minus is shorthand for electrons, then my left side overall would be equal to 0, and my right side overall would be equal to 0 because my positive 2 would cancel out with the negative 2 that's here. You with me? Okay. I hope so. Now, my silvers are going from +1 to 0. How could I possibly balance this with electrons? Well, I'm going to put 1 electron over here, and then this side will add up to 0 because we have 1 negative and 1 positive. They cancel out in terms of charge and gives us a 0, which is equal to this silver 0 over here. Now, something to point out. In this reaction, I want both of my sides to equal 0. In this reaction, I want both of my sides to equal -2. So there's not like a straight up protocol on what's going to happen or what you need to set it equal to, but just know that you can only add in electrons to help you balance in terms of charge. Okay. So this reaction, because my electrons are coming out, my electrons are a product. This means that they are being lost. They're given up. So if this is losing electrons, why is this not typing? This is losing electrons, therefore it is oxidation. This guy is, this guy is gaining electrons because they are a reactant. They're going in, so they're being gained. Gaining electrons is reduction. Boom. Now, some dumb thing that a kid once said that is stuck in my head forever. It's not actually dumb. It's actually really cute. They said, Leo says, girl, because when you are gaining electrons, you'll find them on the left side of the reaction. So that's why your electrons are over here on the left side. So that's another silly way that you can just remember all of this and keep it straight. Instead of Leo says grr, you might like Leo says girl. Maybe that's better for you. Maybe it's not, and that was the cringiest thing that you've ever seen in your entire life. Whatever. So that's pretty much it with half reactions. I gave you an example where you have negative charges. Here is an example with positive charges. If you can follow these steps, the only real new part should be step 4, which is balancing using electrons. The rest of this you should be like pretty good at from the other lessons. So if any of this was confusing, please rewatch. Definitely make sure that you're a pro in determining oxidation states before attempting half reactions, because that's the first step of this. So if you're not good at oxidation states, it's going to be very hard to be successful here. Not impossible, but difficult. So that's it. If you have questions, leave them in the comment section. I will do my best to get back to you, and I will talk to you soon. Bye.